Hi, my name is Sarthak Mohapatra, and this is my submission for Lab 1, Constant Velocity Motion. The purpose of my lab is to compare an observed application of Newton's second law to a generated model. In order to do this, I use the physics principle Newton's second law, which in its prime form is force is equal to mass times acceleration, or F is equal to ma. However, for the purposes of this lab, I had to translate it over into a different form that was more useful. This new form is Vf, velocity final, is equal to Vi, velocity initial, plus Fnet, the net force, divided by m, mass, times delta t, or the change in time. In order to build a model, I used a program called VIDLE and used Python code to replicate this. The total length of my model was 1.367 seconds, which I used in the while loop to maintain the time. In this lab, because there is no acceleration or net force, I set the Fnet to vector 0, 0, 0, so the velocity would be constant. After that, I used ball velocity is equal to ball velocity plus Fnet divided by ball.m times delta t. This is the general form of the equation and is useful to have just in case for future experiments if we have to have different velocities and we have to take into account acceleration and net force. However, in this case, this line is not necessary because Fnet will always be equal to 0, so the ball velocity remains constant. The next line is the ball position. This line sets the ball position equal to the previous position, and then it adds to it the velocity times the change in time. Finally, it takes the final step by adding the next increment of time. This is a video of Tracker where I have tracked the ball and I have plotted the different data points. Now, in order to use Tracker, I had to provide a few different things. First, I had to specify a scale. In this specific video, I found that the size of the object was 32 millimeters long and used that as the scale. I also realized that the ball did not move in a perfectly horizontal motion relative to the camera's angle, so I had to offset the axis a little bit in order to maintain as minimal of a change in the y direction as possible. Because in this case, we only want motion in one direction, which I have set in this case to be the positive x direction. This is a video of the model that I created using Python and VIDLE. Now, here's a graph that compares the experiment's position to the model's position. As you can see, the actual experiment's prediction, what I observed, was a little bit different from the model's position. Now, I think there are a few different reasons for this. One of these reasons is because of the friction force. As you can see, in real life, in the real life experiment, friction creates acceleration in the negative x direction, which creates a lower slope in the graph. The reason this is not as observable as it otherwise would be is because of the relatively small time scale of the graph. Over time, however, it is likely that the experiment, instead of continuing on in the same direction, would slowly slow down until the position would stop changing over time. Another thing that causes a slight problem is, as you can see in the middle, there's a slight bend to the curve. This is caused by a fault in the linearity. If you looked at the video carefully, you'll see that the object does not follow an exactly straight path, but actually curves backwards a little bit. And when this is tracked with Tracker, it creates a slight slowdown, which could be responsible for this problem in the curve. But besides that, I think it is relatively accurate and is a good model. Now, what if? So you'll notice that I used a slightly offset from horizontal x-axis in this case, so just to minimize the movement in the y direction to create a better graph and a better model. Using a different axis like y or z would produce a similar result. I just chose the x-axis in this case. Flipping the axis would also mean that velocity in motion would be in the negative x direction instead of positive x direction, but everything else would be the same and it would create a similar graph just in the other direction. And what does it mean? We don't know all of the different pushes and pulls in the observed case, but we do know some. We know that there's a normal force and a gravitational force, for example, but in this case, because there are so many different forces, they're not really important. All we really care about is the net force, which in this case is 0. Thank you.